Hi, I'm Thomas Power and I will be talking about this work, Data Efficient Control from Images by Learning How to Use a Simple Model. The goal of this work is to learn to perform a control task from image observations with high data efficiency. Using image observations is attractive in situations where we don't have access to the true state representation of the system, for example in the case of deformable objects. Data efficiency is important for real robotic tasks where data collection can be expensive. One current approach is to jointly learn a representation and dynamics with which to do planning and control. This often requires large amounts of data. Our approach is to approximate the system we wish to control with a system that has known state representation and dynamics. We then use this approximation to design a control law using model predictive control. We use online data to determine where this approximation is accurate and bias the controller away from inaccurate regions of the simple model state space. Our approach can be split into two phases. Offline, we learn a state estimator, which estimates the simple model state from image observations. We assume we can generate observations of the simple system which are visually similar to observations from the true system. We train a Sion on ensemble state estimator on these generated observations. We then use the ensemble variance as a measure of how well the simple model state represents the true system at a given instant. Online, we use this state estimator to attempt the task generating data from the true system. We then use this online data to learn where the model approximation is accurate by predicting the future variance of the ensemble estimate. During MPC, we place a cost on transitions which have high predicted uncertainty. We evaluate on a 2D rope manipulation task. The system consists of a mass on the end of a rope, and the goal is to hit a target with the mass by applying force to the base. The simple model approximation here is to treat the rope as a rigid link, and hence the system as an inverted pendulum on a cart. Here we see that predicting and penalizing future uncertainty leads to behavior which keeps the system within the regime which has good correspondence with the simple model. Without this, the system can enter regimes where the simple model is highly inaccurate. Both of these examples successfully complete the task, however. We benchmark against a model-based reinforcement learning method which jointly learns a state representation and dynamics. We pre-train this baseline on the simple system before applying it to the true system. Our method achieves better success rate with an order of magnitude less data. Thanks for taking the time to listen. If you're interested in talking more, please come talk with me at the virtual poster session or reach me by email.